let's begin our discussion today of our last topic, which is bivariate data.
Mr. Chase, is there a note sheet for this one?
Oh, there it is. Yes, thank you. Every teacher needs one of you in your class. Here you go.
Oh, yeah. Is there a note sheet?
You have to burn off a little energy. Do it quietly, though, Isa. All right. All right, listen up. So, in the warm-up today, hopefully you did all of this successfully. I just want to make a note, though, that the kind of data that you engaged with is actually the kind of data as simple as it might have seemed, and as simple as a scatter plot is, and I think most of us have worked with a scatter plot with two different variables happening at the same time. In this unit, and in the last, we haven't dealt with anything but univariate data, that is one set of data. You might be thinking, well, wait, we've done charts like this before, but those were all one set of data. That was values and their frequencies, but that was still like one list. It could be listed all by itself in one list. Think about like the, I don't know, the kilowatt hours usage, right? You had like values and their frequencies. But if you were to actually go back and list it out, all you really have, though, let's keep in mind, is like whatever, 60 or what was it, 60, 50 houses worth of data. That's all it was, is like a list of a bunch of things. And the only reason we put it in a table with two columns is to more quickly summarize it. But honestly, this is the first time we've encountered like two side-by-side variables that we're kind of keep track of. And that's all that's meant by bivariate data, is these two separate variables that we're looking at. So the scatter plot's pretty obvious what's going on. The linear regression, I think you understand why that should look the way it does. You're not maybe sure how the calculator comes up with it, though. So we'll have to hit that first. And R squared, we'll have to explain what those mean. So right now, all of this is just a black box to us. And I'm not going to do a great job of explaining it, because we're going to do like another like kind of entire stat unit in 20 minutes. Okay, here we go. We're going to go super fast and just like try to do the flying overview. So first of all, where does the calculator come up with that equation? The slope and the y-intercept are calculated in this way. And these symbols should many of them should be recognizable to you. Now the subscript is necessary, you can imagine, because we've got two sets of variables. So mu x, mu y, you can see why that's necessary. Well, because there's a mean associated with the x values and a mean associated with the y values. So that's where these come from. Sigma x is, of course, the standard deviation, or sigma x squared would be the variance of the x list. The only thing that's a little weird in here is this mu xy. And that's the mean of the list that you would produce if you multiplied the x's and y's by each other. And this together in the numerator gives you something called the covariance, which is not a word you need to know. I just thought you would like to know that that's what it's like. Okay. More on that if you take other stat or probability theory courses. Notice that if you were to do this by hand, you might calculate the slope first. And then notice that that's used in the y-intercept in the calculation. Anyway, so you could maybe calculate, oh, by the way, all these things, if you do two bar stats on your calculator, all of the things listed here, all the constituent parts are on that list. You can calculate it in that way as well, including mu xy and stuff. Okay, so I think that's all I want to say there. There's still like questions about like where those come from, and I'm punting on that. Sorry. Okay, so but we could chat sometime if you want to come by. If you know another formula for doing that by hand, it may look a little different, and just know that there are a couple ways of thinking about it. The way I wrote it is correct, but there are other correct ways to write it down. We should say what that is. It's called Pearson's product moment correlation coefficient. You don't have to memorize that, but okay, that's what's meant by it. They will actually ask for that. They'll say all of that. They'll never ask you to say it, but on the IB test or something like that, they'll say like write down the value of Pearson's product moment correlation coefficient. So it's a single number that gives you a summary of how close your data is, your one variable is related to the other. The correlation value is between -1 and 1. You just saw in the warm-up that we got like a negative value. It was fairly close to -1, so that means it's a good correlation. So strong correlation if closer to negative or positive 1. A negative correlation indicates that the line goes downhill, right? It's a quick way to say that. For every increase in x, the response in y is a negative response. The slope is negative, if you like to think about that too. It's also important to remember, of course, that correlation does not imply causation. I think you've heard that many other times, and especially those in stat. Who has a ready example of spurious correlation? That doesn't actually. Two things that would have a very strong linear relationship, perhaps, very highly correlated, but aren't causal. You have one?
Ice cream sales and the number of schools open.
Okay, I have one very similar to that up here. I have ice cream sales and the number of sunglasses sold. Yeah, but what's the underlying variable?
Increase in membership.
Yeah, it's the fact that it's like summer, right? That's not, it's not like every time that you sell more sunglasses, people are like, you know what would really taste good right now with these sunglasses? Ice cream. It's not like that at all. There's no causality here, right? Anyone have?
Wait, no.
Okay. Anyone have another example of something that you've heard of and maybe like or in your stat class or usually?
Remember when we were looking at like the names and like age correlation, how like some like names are more correlated to those people, and like some are more correlated to one people.
Okay, but that's not like because you're old, it doesn't go not cause of
Right, like because
your
the
age.
names then.
Yeah, it wasn't. That's an interesting one. Yeah.
The purchase of sweaters and the purchase of heaters.
Go up and hit when, yeah. So you're kind of taking the other approach here. Okay.
You already know.
Thank you for being sarcastic, please.
All right. Good, and there are others too, right? I'm trying to think of what was the one that I saw. It's fun to see this against real data, like sales of Microsoft Office and like murder rates or something like this. It's like completely like super linear, perfect correlation or something, but like I don't know. As far as we know, there's no causality. I'll define that one somewhere. All right, on the slide up here, I also have, you have in your notes, the formula for this R value. You'll notice the numerator looks familiar. It's the same numerator that you saw on the last slide. It's the covariance over, now here we have sigma x, sigma y, the standard deviation of the x times the standard deviation of y. Again, we're not like saying much more about, there's so much more you can say about these things. R squared, this is good for the AP stat people to review. Remember, this is the thing you have to like be able to say word for word. This is a single number after squaring the R value from the last slide that explains the proportion of the total variation in y, the response variable, that can be explained by this linear relationship that we just derived, say, in the warm-up. Right? So once you come up with that linear relationship, what does R squared mean? Explains the proportion. You could say, yeah, sometimes it's maybe better to say the percentage, or it is the proportion. It's a percentage that's between 0 and 1. Of course, it's positive, right? And again, just like on the last slide, if it's closer to 1 in absolute value, then of course you get a better fit. I'm going past that slide. You have all the notes right there. The residual plot is another way to analyze how good of a fit you have with your data. And I think if you either have taken AP Stat or if you had AAF last year, then you would be familiar with residual plots. And if you're a freshman, you don't, I don't know. But it's a pretty easy idea. It's just we're calculating kind of the difference between the data and the estimated data. So how would you actually do that? Reach on your scatter plot. I still have this data from the warm-up up here. You might do this if you're comfortable with list operations, right? If you go back to your list editor, here you've got L1 and L2 still in there from the warm-up today. If you go to L3, and remember you're blinking up on L3, the actual definition of L3, if you make it Y1 of L1, let's stop there for a second. What does that calculate? That calculates if you have your, provided you stored your regression in Y1. That's an important thing. If you stored your regression in Y1. What does this do? It plugs these values into your line to get what your line says the Y value is, right? And then here's the actual Y value in L2, and we just compare, we subtract. How far away is the computed value from the line from the actual value from the data set? Right? So it does that for all these values, and you'll fill in a list that gives the distance from the line that each data point is, right? And those are called residuals. It's a good name for it. And if you were to plot instead, go back to your stat plot, and instead do L1, L3, and plot these residuals, you would get a residual plot that looks something like this. And this is a really nice residual plot. Very, very small residuals. Obviously, you want the errors to be small. But also a random scattering is ideal, too. If you see some kind of pattern emerging in the residuals, that's a bad sign. You might not have noticed it at first, but sometimes you pick it up in the residuals. So if there's some kind of systematic error, sometimes the residuals show that better. And I don't have much more to say about the residuals. Except I will say that if you ever do want to look at the residuals, there is a faster way to do it, too, than it's not very hard to do what I just said. But there's actually, every time you run a linear regression, your calculator puts into the list menu a list called resid. And so if you just want to plot L1 and then resid, you can grab that from the list menu on your calculator. It won't have been there unless you did a linear regression at some point in your life. And then it'll actually plot these for you, too. It always calculates this residual list for you. So try this with this new set of data. It's on the top of the third page for you. Okay. Run, do the same thing. This is good. Just clear out L1, L2, L3, all those. Clear those out and put this in L1, L2. Do it quickly. See how fast you can do this. Do just again like the warm-up, a linear regression. And either by hand do the residuals or use just the resid list. And think about how good of a fit this is. I want you to think about how appropriate you think the fit is for this set of data. Use it. Your ear. So great.
Dinesh, was that in your eye?
What?
Big mistake.
Oh, no. Oh, that's not linear.
Anybody have a beautiful residual plot?
I didn't
That's dangerous. Right? What do you think about what do you think of those
I think it's not linear. I think there's a noticeable pattern in there for it.
You guys agree with me?
I think Abe's a brilliant guy.
Super humble.
I think eating.
Super humble. Do you get a plot that looks something like this for the actual data? And then yeah, as Abe said, there does seem to be a pattern in the residuals, maybe. So let's take a look at those as well. When you run the linear regression, you can actually already start to see it sometimes in the linear regression. It's just the residuals, really, if you feel they're necessary. They do make it a little more obvious. Pattern in the residuals. So let's take a look at that plot too. Did you get something like this for your residual plot? Yeah? So that makes this not linear. What are we talking about here? Water in an urn? There's definitely trouble in the water. It's not linear.
What? Observed minus predicted.
Well, what could you do besides just throwing up your hands? One thing we could do, I kind of want to go back and look at the data a little bit too here. It does have this kind of downward curve, so you might try some kind of curved fit. What did I say? L2 minus Y1 of L1 is maybe what it should say. Yeah. In the end, it'll just be like this. Then, yeah. So what can we do on this last example? Let's keep working with this data. It looks like it's curved, but we don't want to just throw up our hands and be like, well, we tried linear. It didn't really work. Let's go home. Well, let's try to do something. Let's try to resolve the situation a little bit. So one way we can maybe do this is to do something called re-expression. I'm going to manipulate the data a little bit here. We think that it looks perhaps not linear. Perhaps it looks like there's a slight curve to it. Maybe it's, let's try first, assuming maybe it's quadratic. So if we do what I'd like to start by doing, hopefully you're getting good at these list operations. In L1 and L2, you've got your data already. Those water earned probably just we're working on. In L3, could you put the definition of L3 as the square root of L2 and populate that? The reason is because I'm thinking that maybe this data is quadratic. Maybe if I take the square root, then maybe I'll get something linear. My hope is that it'll be more linear, perhaps. So now run the regression this time, but not with L1, L2, but run your regression with L1 and L3 as the y values, okay? L1 is the x value still, but L3 is the y values. And tell me if you do or don't get this equation right here. Do you get negative? Try it someone. Tell me if you get negative 0.005 and 3.529 as your values. You want to confirm that? Okay, thanks. Now, when we write this down, if we're going to write this down on our paper, we're not going to write y equals negative 0.005x plus 3.529. We're going to write, because that's not what we did. We didn't run a regression on x and y. We ran a regression with x and root y. So this is what maybe you need to write down, right? And now, what's y? Well, of course, it's very simple to solve for y in this particular instance. You just do what on both sides? Yeah. So squaring both sides recovers an equation that in fact is quadratic now. So, and I think if you already checked your r squared value on this one, it's a much better fit. And now if you wanted to get, so hopefully you see the cycle we've just been through. You had some data, you took the square root of the y values, you ran a linear regression on that, it was really excellent. Yay. And then you took that result, though, and said, well, that's not really, in the end, what we wanted, because that was not with the data. That was with the data with the square root of y values. Well, that's easy. We can just recover, and now we have this nice quadratic model. So we took the square root of the y values, did a linear regression, and then we came back to our data with a model that works better by taking the y values and squaring them again, right? And if you go back to the original data, plotted nicely, and you plot this thing squared, I think you'll see that it cuts through the data very nicely. We just did a basically quadratic regression, but by hacking the linear regression on our calculator. We still have a question about whether, in the end, we just do everything we can in the name of getting a really good fit. Yeah. Yeah, and in fact, I'm going to do a couple of these things in the background to show you how those work. We're going to next do an exponential regression, but we're not going to use the exponential regression. To show you how to use linear regression, and then eventually you can just do that too.
Yeah, I'm kind of lost. So I know that you have the square root equals that equation, and then you have to square it to get. But what exactly do you square?
Both sides of this equation.
Okay.
So
How do you do?
yeah, I know I should have it written up here. So the actual quadratic equation that you're getting is this one. So on your calculator, if you have the original data and then y1, if you want to put this, you'll get a quadratic that, my board is not being very responsive. Come on.
Okay, and what do you do with that once you have it?
That's the quadratic regression of this equation. So like I said, if you plot this, you'll see that this is a much better fit for our data actually. Go back to the data, look at it, scatter plot. Plot this in y1 instead, and you'll see that it's like this nice quadratic regression for the curve.
Oh, so can you take an r value of a quadratic regression too?
Anything that can be linearized, you can give an r squared value for, sure, yeah. I mean, yeah, we just kind of looked at it, you mean? And we're like, oh, it looks like it's a curve. Is that what you mean? It doesn't seem very exacting. You're right. Yeah, no, it's a little bit weird that I just be like, let's try a quadratic. And it does seem to be better. In the end, though, let's criticize it, too, because it's not perfect. There's one thing that's especially not perfect about it. what does it actually say about the future, about this urn in the water? Think about what this model looks like using your just Algebra 1 knowledge of parabolas. What does this actually look like? It's going to look like this. And then it's going to go back up, right? Like almost. So if you were to extrapolate even a little bit into the future, you would just get results that are not very useful or reasonable at all. So we still have questions about the domain of valid validity for this and whether, like, how much we can trust this. But it does seem to at least give us a better R-squared value. So that's good, but you know, you might be like, well, why don't we try a cubic? I bet we'd even get a better. And the answer is like, yeah, you probably would. It's not perfect. It's not the being all and end all is not like fitting the data necessarily. But we do kind of maybe think about the data in terms of what we might expect it to be too. So I can see why you might be thinking, well, there's a slight curve to this population data. It's on the next page there. But you also might not be first inclined to give a quadratic model. So I think a lot of us, having studied population models, might be like, well, I'd like to try an exponential model. But let's say again that we don't have access to our exponential regression. We want to like think about how your exponential regression even works on the calculator. So it's not bad. If you think this is exponential, then so go ahead and, if you haven't already started doing this, L1 and L2 on your calculator. And in L3, if you think L2 is exponential, then how do we undo exponentials? Yeah, just take the log of L2 as your L3 column, okay? And by the log, I mean either log base 10 or natural log. It doesn't matter, because afterward, after you've done your regression on L3, when you come back to your original equation, it'll matter what you did, right? If you did the common log, then on the way back, you'll be doing 10 to the to recover your equation. And if you chose instead to do the natural log on the front side of the problem, then on the back side of the problem, when you're coming back to you'll do e to the to recover your equation. So L1, L2, and then in L3, do the log or natural log of L2. Just like we do with the square root. And by the way, if you're doing L1, are you putting in those values, or you want to put in 0, 10, 20? What do you want to do? You can do whichever you like. It's up to you. Doesn't matter. Let's see you actually look at yours on this. Okay. Whatever you like. Compare with the neighbor. See if you get a really good fit now, because it should be that you get a decent fit.
Okay, I got this. I don't think that's right.
And then maybe you can already be thinking, how do you recover the equation? Maybe you can think about how you do that. You can do the natural log or the log. They just differ by a constant. No. Right. Someone want to give me the regression equation they got? We'll do the re-expression with your equation, whichever it is. 0.00 8.68. All right, we'll just pretend whatever she says is the truth. I need to know what you did to your y values. What did you do to your the log base 10? All right, so again, you want to think, okay, if that's what you just got, again, it's not y equals that regression. It's log base 10 of y equals that regression. But that's not a big deal. It's easy to recover y. And you can see in a second that it really, Ms. Chase, is this going to be an exponential equation when we're done? With like a something times a something to the x? And the answer is yeah. Let's see if we can get it. So how do we recover y here? We do what on both sides? Yeah, 10 to the, right? So over here we get 10 to the, all this. It's not maybe obvious what we have here yet, but this is 10 to the negative 8.68 times 10 to the, if you use laws of exponents here, 10 to the 0.00557 x, right? And actually, if you have power of a power, that's multiplication. So can you see, maybe that's actually this to the x, right? To the x. So actually we do have something of the form a times b to the x, right? Where this is your thing out in front of the exponential, and this is the base of your exponential growth. Do you see it? Now if you used natural log all the way through, then you just have an e here instead of a 10 in both these places. Okay? But you should, in the end, all of us should agree on the answer to that. All right, do the best you can on the back of this especially. The one thing we didn't get to talk about a lot is this table. There are a couple transformations of the data. We didn't talk about the natural log or the power one. So take a look at those and see if you can interpret how you would handle if you thought you had what might be a power model or a linear or a natural log. Hopefully you recognize the other transformations of the data that we just did though.
No.